thank you for joining, Jose and Alex. So today this will be a bit different versus the other LAR talks we had. So we will do this in English. I would say that it would be more or less the same format and the same 60 to 90 minutes. And today we are going to focus on immunology and its relation to some diseases and trying to explain what this is and what actually the researchers are doing about it, how they do it. And then after a brief introduction, we will basically have a conversation between the four of us. So we have the two expert people here, so Anna and Alex, and then basically the two, I don't want to say dumb people, but when it comes to this subject, I would say that I'm the dumb one. Jose, I guess you are less of a dumb one on this one because, I mean, you studied something related more or less to that, right? So, but I will let each one of you to present yourself so that at least the people that are watching us will know you better, and then we can start with the topic itself. So I guess Jose, if you want, you can start.
Sure. Let's throw the new guy under the bus.
Exactly.
Take it out of the way. So my name is José Pérez. I am a pharmacist. I've studied pharmaceutical sciences. I'm currently working in Brussels in a consultancy, public affairs, healthcare public affairs. And that's it. On the immunology side, I haven't properly worked a lot. Currently, I'm only working with European policies like the European Beating Cancer Plan and on that front. So I am one of the dumb ones. I am not an expert on the issue by any standard.
Yeah, but you are the second less dumb, I would say.
Oh.
You know, it's like
I'm not gonna take that as a win, but okay. Sure.
You know, it's like yesterday. Actually, we were preparing this talk. Me, Alex, and Anna, and we went with some other people to a bar. And actually, it made me remember that Alex first he started. So I want to drink something. I want a wine, and then he ordered. I don't want the cheapest one, but the second cheapest one. And then you went for another glass of wine, the third cheapest one, which maybe it's the most expensive one. So, you know, so it can be a compliment.
It was definitely better than the second cheapest.
You see?
Pretty nice.
So I think now it's your turn, Anna.
Okay, so my name is Ana, or Ana Rita. I'm doing a PhD. So I'm a PhD student in the Free University of Brussels, the VUB. And I work in an immunology lab. And in my case specifically, I study brain cancers, both in animal models like mice, but also in human samples that we get from the hospital. And we try to understand which are the players, so let's call the cells that help the brain cancer to progress. And also we try to, using different techniques, of course, so for example, if we take out one of these players, does the tumor grow slower or not? So it's still quite a fundamental stage, because what we want to do mainly is characterize this tumor at the level of the immunology. So if I use if I use any word or something that is really not understandable, just ask me so that I can say it in a more layman way.
I will be that person. Don't worry.
Okay, good, Miguel. Good.
Cool. Yeah, I'm Alex. I'm probably the reason we're doing this in English, I guess.
Probably.
Looking around. So yeah, I'm also a PhD student. In my third year in the same university as Anna, in the same lab, believe it or not. You're not going to get some different opinions from the two of us, that's for sure. And yeah, I also study how the immune system interacts with tumors and then how we can exploit these interactions in order to fight cancer.
Okay. Very good. So, and do you want to tell us a bit more about you? I mean, where are you from? I mean, you are the only one that it's not Portuguese, so I think it would be interesting to know your roots.
That is true. You're not that dumb, Miguel, if you noticed that. No, I was born in Serbia, and then when I was 5 years old, my family moved to Australia, and I was raised in Australia. And then 5 years ago, I came here to do a master and fell in love with the beautiful summers that you get in Belgium. I mean, oh my God. I mean, pouring rain.
Yeah.
If you're lucky, because usually it's between 17 and 18. So
Yeah, and then what quickly turned from a 2-year master program with dreams of going then to another warmer country, it's turned into 5, 6, 7 years.
A 6 years PhD nightmare, basically.
That's tough.
Yeah. Okay. Yeah. Very good.
So
very
far.
good. Yes. Yes. Exactly. So I think like we talked before. I think you both. I don't know. I think you between each of you will organize yourselves who says what. But I think we can start with explaining a bit what is actually immunology, and everyone knows about the immune system, but how does it work? I mean, explain me like I'm a 5-year-old, basically, you know.
okay. Right. Okay. So of course, immunology is the science or the discipline that studies the immune system. But so what is the immune system? The immune system is something that is in our body and actually protects us against invaders, pathogens. But even just when you have like a simple wound, the immune system will enter in action and will help you heal this wound. So, and it's also very important that we know that the immune system needs to be extremely balanced, because so we cannot have an overactivation of this immune system, but because it can lead actually to disease that we may talk later. But we also cannot have an immune system that doesn't do anything, that is just patiently looking at us getting sick, let's say. So it's a fine balance to keep everything stable. But so if we would have to explain in an easy way how actually the immune system works, let's put it in this example. So you have a robbery. You're being robbed from your house. So the first thing that these robbers encounter is your door. And this door is a bit like your skin, you see? So it's the first thing that avoids direct contact between your body and the exterior, right? But sometimes these robbers can go through the door and then they find you. And you actually are the first person that can do something to fight these people that get into your house. But sometimes you are actually not enough, right? I mean, you cannot just fight robbers.
I mean, first I would ask them to take off their shoes, right? I think that's the first thing.
I think the immune system maybe also does that, actually. I think they first have a little, so exactly, there's a little conversation that tries to say, hey, man, I mean, you should leave. But sometimes it doesn't work.
Dude, I have a huge OCD. Please take off your shoes, you know? Like, yeah, that can happen as well.
And then if this doesn't work very well, what happens is that actually you call the police. But when you call the police, you actually have to explain them what is happening. You have to describe this invader. And then the police will come to your house, recognize the risk, and then take an action and arrest these people. The same happens in our immune system, right? So the immune system first recognizes the problem through certain players or certain what we call cells. But sometimes these cells are not enough, and therefore then new cells need to be activated to have a response that can lead them to actually kick out these invaders from our body. And so this is always a very streamlined and organized way of action or process. And also, so it's important that if that nothing goes wrong, right, in this communication and how these cells act, because in this way that if something goes wrong, that diseases may occur, for example. And we have diseases like everyone knows, like multiple sclerosis, we have cancer, or even a simple flu. All of these kind of disease lead to an activation of our immune system. Not always our immune system can deal very well with them. Something also important that our immune system does is that it actually is capable of memorizing, let's say. And how so? For example, if you are in your job, right, and you, for example, you have a problem, you solve this problem, right? 2 weeks later, you have again a problem. Actually, you're going to be much faster to solve this problem. Sometimes it's not even a problem anymore. And actually, this happens on a daily basis. So on a daily basis, we encounter different types of pathogens, of invaders, of, viruses, but sometimes we don't even have symptoms or we don't even feel bad because our body is so good actually at fighting them and at kicking them out.
Yeah, so basically these are the post-its that I have all over my computer, right? I mean, because I don't have a memory. So if you need to have something that will help you to remember that, right? I mean, I guess.
At least it's not tattoos over your body like that guy in Memento.
Yes, or Prison Break, you know. Yeah, yeah, that's also a good point. Yeah.
Yeah, it's a good way of putting it, Miguel. Actually, so you can say that we have certain cells in our body that are full of these post-its, and then they quickly see, did this happen? Did this happen? Yes. How did we solve it? Yes, we solved it like this, and then they take action much quickly. Or if we even still get the policeman metaphor, of course, if the police already know how to act against a certain kind of problem, they will do it much faster. While, for example, if they never encounter a certain problem or a certain situation, they will take longer because they will have to discuss about it and so on. But that's why our immune system is so, clever, and now it's so evolved actually, because it has these ways to be able to help us to not be sick all the time, let's say.
Jose, you have some questions?
Who's our sponsor for the break?
Sorry?
Who's our sponsor for the break?
That's
no one.
Insert sponsor. We are still looking for a sponsor.
Sorry.
If we had a sponsor, we could pay the premium Zoom, you know.
Whoever is watching, who wants to be our sponsor for 30 seconds? Please.
Yeah, that's a good point. Yeah, indeed. So I was reading some comments on the chat, Jose, and I think there were some followers that wanted to hear your voice.
That's a mistake. That's probably a mistake to follow. Normally, every chat box, not only this one, it's always a mistake. Don't see comments. Just stay out of that zone, please, for everyone's sake. I was just enjoying the analogy, but what else? What else do Miguel? Tell me you. What's the follow up? What's any?
I have one thing. I mean, I was reading some news before to try not to be that dumb in front of you guys, and I read something. I read something that it was talking about this question of how forgettable can your body be for a certain virus. For example, can your antibodies fade away so that virus that you had immunology, you know, right? So you could resist to that immunity, exactly. You could resist to that virus for a certain period, but then it's like your body forgets and then you cannot resist anymore. And actually I read it because, you know, nowadays there are a lot of news about health problems. I don't know if you heard about COVID-19. I think it's something, I think they call it coronavirus. So it's a virus that apparently, before they were saying if you get it, you get good immunity, but now they are doubting maybe you don't get immunity, maybe your body will forget how to resist to the virus. So the question is, how do we know and how do we test if a virus has the possibility to be forgettable or not? You know, is it just by experience over time, or is there something that we can do at the start of when we discover some virus? Like, okay, I know that if I do the XZ23 test, this virus will tell me if it is forgettable or not over time. So.
Yeah, I mean, in general, the way that people look at this is they measure the antibody titers. So the amount of this specific antibody that's in your blood. So if somebody has coronavirus, I think there are a fair few currently known neutralizing antibodies that a lot of people can develop. And then you can measure the specific levels of these antibodies. And so usually when somebody is going through this infection or has just beaten this infection, they should be quite high in the blood. And then as you distance yourself in time from that infection, you don't need them as high anymore, because whenever you switch on this immune response in your body, you also have to switch it off. Otherwise, well, you know, you'll always be sick. And so then these antibodies start to fade from the blood. There should always be, I think, a very small level to indicate that there is still a memory. But in general, I think the way that you can increase this, so there's a pharmaceutical company at the moment, I think they're entering phase 3 trials of their vaccine, it's Moderna.
Yeah.
They see that the best antibody memory, or the highest lingering antibody levels in the patients they've tried so far, they give 2 shots. So after the first shot, there won't be very many antibodies. But after the second one, then these patients that have been vaccinated have higher levels of antibodies. I think it was 57 days later than patients who've beaten the coronavirus. So while they're not sure if this is going to be enough, they're fairly happy with this beginning.
Okay.
So it's very hard to say what defines why you have a very good response. I think it's in the initial stimulation of the immune system and how potent this virus is, basically.
Yeah, and now, for example, young the virus is, and how easily it can mutate, and therefore, if you encounter this virus is not exactly the same as the one before. So it can be just evolution. I don't know, like the many years we will counter this virus, this protection of our body will become better. Because what I read in this, I think it's the same thing that you also read, is that, for example, against measles, our immune response is really good. So once you get once, like you're very good at not getting it again, basically. So I think I don't think you can know per se in advance how it is. So indeed, I think you have to study the people who get the disease, the virus itself. But when a virus comes out, you cannot just simply say, yeah, this is going to work or this is not going to work, I think, in general. And that's why research is very important, guys.
My connection is kind of bad, so if I stop mid sentences, I apologize. But yeah, it's probably going to happen. It's probably happening right now, isn't it? Sure, why not?
Yeah.
Thank you.
Thank you.
No, but
so did you understand the question?
I understood everything. No, but just in this regard, that was one of the hopes when Corona started, at least on a more popular sense, that we would develop an immunization that we would be off, and that's why there are things like, and this influenced the debates when you go to the UK about herd immunity. It doesn't make much sense talk about making policies that are going to affect your population on a basis until the vaccine is developed. If you are not sure, which is the case, now we are a little bit more that you are not immunized for life. It's not going to last. And at the time, that was at least the hope when it started, that I get COVID once, and hopefully for the rest of my life, at least I am not going to get it again.
I'm
Yeah,
COVID
yeah,
free. I'm COVID free.
exactly, but that was the hope. You are not afraid to get certain kinds of diseases
That's
again.
true. And I mean, I think also like people, and myself included, we didn't really understand that. Okay, you get COVID, you are let's say cured, and then it's okay. But actually, there are a lot of other diseases and problems that can come because of that. I heard like diabetes. I heard like other type of chronic issues that you can get because of that. So it's not just like I have coronavirus now. It's okay. I don't have it anymore. I will not have it again. Probably that's not true, and I will continue to be as healthy as I was. Probably not. So yeah, I think it's important to inform people and to get informed through the right sources. Not like going to Instagram and checking the memes and see, oh, well, yeah, maybe, I think there's a lot of misinformation, and that's something that we were talking yesterday, me and Alex, about that, and the way the media also share the information, it needs to be, they need to be very careful and very critic on what they are doing. I'm not saying everyone, but sometimes you share things just for the sake of clickbait, just for the sake of selling views, and for me that's not right. And I just wanted to hear from each one of you what are your opinions about it as well. The way science is being shared all over the world. I mean, we are talking coronavirus, but we can change the topic, right? Because we all talked about it for too long already. But I wanted to hear from you what you think about media and the way they share the information regarding research and immunology, for example.
I think the problem is, of course, is that there is a lot of demands. So people want to know, right? So you need to give them fast answers. And science is actually a slow process. This means that when COVID-19 came out, everyone became very stressed, or initially no one really cared because it was not really here, a few cases. But once it boomed, yeah, it became such a demand for information that everyone seemed to understand everything. Everyone had an opinion. And some of them were actually valid, because, for example, you're talking about herd immunity and about how we could actually become immune, but actually this happened because before, with other flus, this is what happened, right? And actually you should be able to be in contact, let's say, with the virus, in the sense that indeed after a while it will just become like another normal flu that we have. But the problem is that sometimes I think the media, as you said, just because of views, they release a news, they release an article without really checking with people who actually know, with researchers or professors, or even people who work in pharmaceutical companies. And this can be a huge problem, because then people become aggravated, and then people don't really know what to do. And that we have actually organizations like the World Health Organization that can give reliable information. So it's just that there must be a better coordination, maybe between scientists and also the newspapers or the channels. And maybe that's also a bit our fault, right? Because sometimes we don't promote as good as we should what we do and what science is and so on. I don't know. What is your opinion, Alex?
Oh, excellent. You could be the host, Anna. It was very nice.
Yeah, next time, Anna, will invite you to be the host.
No, I think it's quite difficult when there's a new virus that nobody's seen, and then with policy making, as you mentioned before, I think it's really hard to navigate a ship when you have no idea what a lot of these stories are. And for me, I think there's a demand from public to know the correct answer as soon as possible, which makes sense. But that if new findings come to light, if you change that answer, it seems to be very difficult to get the support from the public. So early on, the World Health Organization sort of said you don't have to really wear masks. Then at some point, they flipped months after they say this, then more data comes in, more understanding, more people get sick, and then the instructions change. And so I don't think the media, at least the media I consume, is built to communicate science, mainly because not a lot of scientists are in the media. And they're also married into a lot of the initial opinion. So if you're wrong from 3 months ago, then you can't, it seemed a bit was weak in terms of politically. I think it politicized to change your response.
Yeah, I mean, unless you say to people that they should drink bleach or get some ultra radiation in your body, I mean, on those cases, I think you should go back.
But this actually, what Alex is saying, is a really big problem. The fact that politics then gets involved in this kind of situation, and the fact that a government is taking some kind of measures, and why the Portuguese government did something or the Belgian government did something else. And all of these then gets a bit in the way in information, which is normal. I mean, we live in a society and we have to, live with all these different players and all these different organizations. But actually, mostly, at least what I think we want to pass is that science is slow. It takes time, and it's normal that things change, because things were not the same 30 years ago, 20 years ago, 5 years ago. So it's normal that things, and actually sometimes I'm afraid that media themselves, but maybe I'm wrong, but they actually, instead of just giving the news, so this is what's going to happen now, they also, which is normal, but they a bit say, oh, but why this was not like this before, and now is changed, and so on. I mean, usually there is a scientific reason behind the decisions that are changing and so on. Usually, I hope. Because other people, indeed, as drinking bleach, I don't think is scientifically approved anywhere in the world.
Yeah.
I don't know, Jose, you work in politics,
Yes.
sort of.
So do you drink bleach?
No, I do not. At least not for now. If my video is going to break, but if my sound is okay, at least tell me if it breaks. It's like a game of a broken phone. It's like a game of a broken phone. You are talking to scientists and doctors, speakers as lawyers, let alone as journalists. The message gets destroyed in the way. Then you have a journalist. Let's assume that the policymaker got the message right, which is far from reality, very far away. But let's assume that he got the idea right, and that he sees a plan, and that he sees where to tackle. Then you got the media. You got a guy from, without any disrespect, you got a guy from journalism that doesn't know what a cell is, trying to explain something that he didn't understood to an audience that, in the worst case, the audience knows already more than what the journalist is trying to say. And the message gets destroyed. And if you want to go to, for instance, because you were talking about the measures taken by the government, we are lucky to be in Europe, where our leaders have been doing kind of a good job when it comes. For instance, let's not talk about COVID, but talking about COVID. In America, in the United States, the conversation it's politics above facts. So you got institutions like the CDC who are amazing, who do an amazing job, but they are getting destroyed by the policymakers. And here, on the other side of the Atlantic, when we are privileged, we have the CDC, which doesn't have the funds, doesn't have. So it's the exact. I hope that I'm getting across clear. It's the exact opposite. Here you have politicians who would be open to listen to an agency trying to put out the scientific approach the best they could. On the other side, you have an agency who has all of the resources, but the policymakers are completely deaf. so everyone is bad.
Yeah.
It's true.
He did freeze in a great frame. Well, yeah.
But it's true, and this is one of the worrying.
I hope that
It's okay. It's okay, Jose. I think we got it. Yeah.
It's one of the dangerous things is when things like this get politicized overly, because the CDC is still a scientific body with its own integrity. They run themselves basically. And so I think I was just reading recently that the instruction has changed in the USA now, and that all new COVID-19 cases in the USA from hospitals should be reported to the HHS first, and then this information will be given to the CDC later. This is something that's extremely dangerous.
Maybe you should explain what is the H.
So it's the health and
yes, we haven't said what CDC or the ECDC were.
I was about to ask ACDC, but what do you mean? Is it the band? Do they work in science as well, or?
Yeah, sorry, that was a gap. It's the European Center for Disease Control. It would be our CDC, our Center for Disease Control. But here
ECDC,
in Europe.
okay.
ECDC, European Center for Disease Control, which would do for instance, in a pandemic, they should be at least, or they could be the first line of defense to gather data, to develop a strategy, to at least advise the policymakers, to do all of that homework. But the ECDC doesn't have the proper funds that it should have, and that's one of the main discussions that is happening right now. That's one of the few times that there is really a lot of political consensus. The ECDC is getting a lot. It will be a lot stronger after this. But if you go to the United States, the data that is collected for you to put out and to develop a policy, there isn't. The data, it's complete. The CDC, it's getting murdered by the administration. It's awful to see. So if you want to go to the media, to go back to the conversation, how are they going to report the things right if the CDC can't report properly to the government?
That's true.
Yeah,
you are doomed from the start if you don't give them the proper tools to do their job, or if you ignore them, which is the case. Awful. So sorry to be the pessimist here.
No. Someone needs to be the pessimist, you know.
Sorry.
Yeah,
I'm not usually that one.
I mean, it's not about being the pessimist. It's just about looking at things with the right glasses, right? So I think it's a very peculiar theme, and today we don't really see how we can effectively change it. Maybe trying to impose somehow to have people I know that Anna is interested on that, about the way you communicate science, right? So actually you can be a scientist, you can be a researcher, and you can work in a lab, but you can also have very good, let's say, soft skills, presenting skills, how to show the work you are doing to a huge amount of people, and that they can listen to you and they're like, well, that's nice, you know, and not just doing a paper with, you know, numbers and things that 99% of the people don't understand. So I think it's one of the fields that it's very important, and it should be, in my opinion, one of the best ways to start pushing science into the overall society, so that everyone understands it in the right way, and so that we can influence the way media shares it as well. There is one thing that I know that we wanted to talk, which is related a bit to this, going back again to immunology. How do we study that, and how when it started, what was the process that led us to be where we are now, and how over time did people study these things, and how did they evolve until this point? And in your opinion, what would be the future for it? If you have, I mean, if imagine that you are in an interview and I'm gonna ask you, so Anna, where do you wanna be in the next 5 years? Where do you see yourself? You know, a bit like that.
I think I am already practicing for the future that is not long, not far anymore. So actually, to break your question in a few questions. So the first one would be, so how did the immune system started to be studied? I actually have to say that I had to go have a bit of a look. But so one of the first earliest known references, at least about immunity, was actually in Athens in the 430 like BC, when someone noticed that people that have recovered from the plague could actually nurse other people that were sick without getting sick. So it's what it is actually immunity, right? They encountered the virus or the infection and then they recovered and now they actually can treat it. But then we also have later, of course, in 1882, sorry, my English and numbers is bad. How do you say that? 1800s?
1882. But I think both ways are correct.
I think mine is less correct, but okay, let's continue.
Is the second most correct one.
Okay, good. So actually, there was, it's very difficult to say his name, but Eli.
Just Ellie.
Eli. He was a Russian, and actually he was the pioneer to find, using a microscope, actually the first cell or the first immune cell known at the moment. These were actually big cells that could eat other dead cells or debris. And this was actually one of the first or the pioneering work that was done within immunology. For the people who already know immunology, we call these cells actually macrophages, and they are actually the cells that clean our body, and they take care a bit of the trash, and they make sure, and actually the first ones that encounter sometimes the dangers and check, can we manage or do we need to call for the backup? So, and actually because of this, in 1988, he was awarded with the Nobel Prize in Physiology and Medicine in recognition for his work in immunity. And along the time, of course, all of these, the science evolved. We got better materials, better tools, but I don't know if you know anything more.
I have a question. Did the quality of the mice changed, increased? Do you have better mice now than you had before?
Yeah, indeed.
You can say yes. You can say yes. It's true.
There are no right and wrong answers.
But what you would initially maybe test just on normal mice. You would
true.
inject them with some cancer cells and treat them with a chemotherapeutic agent or something like this. Now you can have cancer models that are genetically present in the mouse's genome, and then when you inject them with a virus, they can spontaneously develop a tumor over quite a slow period of time that tries to recapitulate the human situation as best as possible.
Mm-hmm.
So you have these mice that are genetically already predisposed to develop cancer.
So,
or for example,
today you genetically modify the mice so that you can actually do your work in a better way, right?
Some people, yes. What you try to do is take what is happening in the human and try to replicate that as closely as possible as you can in a mouse. Mm-hmm. And so then you can try, at least that's what we do, and so that we can try different therapies out rather than having to try them in humans, because then who knows what can happen.
Yeah. So the mice also is because they are, let's say, the smallest within the smallest animals, or they are the closest to us, for example, in terms of, I'm of course in a very how do you say, not rudimentary, but much simple way. Still, you know, they have their brain, they have their lungs, they have the liver. So you see, they have all these organs that also humans have. So they are very important, or they can be very important to study new drugs, but also just to study any kind of organ at a more fundamental level, let's say. And not only mice, but also we also have tools that evolved along the time. So now we can actually see in vivo, I mean in mice, what is happening through a microscope. So for example, in the case of Ellie, sorry, oh my God. He actually had like probably a smear under the microscope, you know, so nothing was really alive anymore, let's say. Now we can actually see in the mouse when the mouse is alive, or for example, we can keep cells alive in a nice environment that is like 37 degrees where cells are happy. So we can see things actually happening at the moment. So we can see things happening because we have new tools that allow us to do that.
Can you see, for example, a mice with cancer? Can you see the I guess the growth of the cancer a long time? That's
yeah.
Yes.
Yeah, indeed, you can. So with the models that I work with, they're much less sophisticated than genetically engineered mice, but we have transplantable tumors. So I'll just inject a tumor below the skin of a mouse, and then you can just watch it growing slowly and progressing.
Yeah.
Internal models like these you can have them express a sort of fluorescent marker, so that when you look at them through a fluorescent microscope or a body BLI,
yeah.
and so then you can see a signal where it fluoresces.
Yeah. And
it's like infrared. It's like infrared or night vision, right?
Actually can be infrared. So if you actually make your cells express this infrared and then you have the right source of light, you can do it. And for example, with brain tumors, of course, they grow inside of the brain. So this can be harder. And this is one of the hypotheses that Aleks said. But also you have, of course, MRI. So the same people go to the hospital and get an MRI. We can do them also in mice. The only problem is that...
Can you just explain what is an MRI, at least the acronym?
So basically, you just have a picture of what is happening in the brain, you know, and actually, the thing is that also the density of your tumor is completely different from the density of the healthy brain. So you can actually see very nicely where the brain, well, also.
What a nice cancer, man. You got a really nice cancer.
Located. It's quite expensive, actually, MRI technique. So it's always a bit, it depends how much money the lab has, or the research, or the hospital. So, and of course, because,
it depends on how much funding you get from the EU. If it's possible.
Yeah, I don't have great news about that, but
they did fund you an EU flag, right?
This was bought. This was bought.
Oh,
that's the worst part. No. This was bought. This is 2.5, if I'm not mistaken. So yeah, and the Portuguese was bought too. So nothing is free in this life. Just one thing that I don't know if we go a little bit off rails, but I think it's important because it's not exactly immunology, but it's clinical research and scientific research, and for the ones, I don't know if you want to talk about it, but why do you do in animals and not on cells? There are always these kind of questions of that those sound bites that are annoying, and you try to explain and people don't want to hear about it. They didn't even want it in the first when they asked. But why do we use animals? So that people, my mom that's hearing our conversation, can know.
Well, yeah, the easiest thing is that your whole body is always a very dynamic system, and so when you pull on one lever, another lever is going to respond. And so when you change one thing, when you stimulate one cell type, or when you focus in and treat a tumor, there are systemic changes that'll happen in your body that respond to this. So there was one of these issues which you try this first in mice, and then you see that the mice are healthy, you see that it works, you can generate promising data that warrants then trying it in humans. Otherwise, if you try something like some of these more dangerous therapies, then if you just go straight to humans, people can potentially die. No one died a few years, I think it was happened about 15 years ago. There's a receptor on one of these very strong killing cells in your body called a T cell. And when you stimulate this receptor, you hyperactivate the T cell and it begins killing. And so in the case of cancer, it's very good to have this hyperactive T cell that goes into the cancer and kills all of the cancer cells. And so all of the lead up in mice was extremely good. The doses were very well tolerated. The tumors were gone in the mice. They were completely rejected. And as soon as they tried the first trial in humans, it reacted completely differently, and it set all of the T cells in the body of these people just activated and on fire, and they went into a cytokine storm, and all of them nearly died. They all went into intensive care for the next couple of days with the smallest dose. And so even though we have these animal models, it's still not perfect, but this would happen a lot more if we didn't try things initially in other animals.
Mm-hmm. And of course, the future is to try as much as possible to reduce the amount of mice. And I mean, we follow strict rules that are imposed not only by the European Union, but also by our own universities, that we need to fill all the paperwork. We need to justify statistically why we need these mice, why don't we use another one, how this is important for our research. And of course, there are a lot of groups even already working in ways of working, for example, with computers, or like trying to bioinformatically understand what is happening. Or, for example, now we have what is called organoids. So what they try to mimic in a little plate, let's say, is that they put different cells together that are important, for example, in the growth of the tumor, either the immune cells, the cancer cells, or just the cells that support the entire, tumor. And then they try to study it. But still, this is very difficult in the sense, for example, of studying behavior, right? Because all these drugs not only affect that little tumor, they will affect the entire body. They will affect, the way people behave or the way people feel. In this case, we do it in mice, of course, and there are tests that you can do to check how the mice are developing, not just by the size of the tumor, right? So, and another thing, for example, when you study the brain, it's very hard still nowadays to do it in a way that you don't use mice, because the brain is such a complex organ that controls so many activities that, it's still very difficult to...
How do you get a human sample of the brain?
Yes, and actually what we can do indeed is working with the human samples, but this is also quite hard. It's difficult to get enough samples. These people have to be in clinical trials. They have to give consent to give this sample. For example, to get healthy tissues, this is almost impossible. So the more health you can get, I think, maybe I'm wrong, but it's people, for example, with epilepsy that they need to go under surgery to remove a certain part of their brain. Sorry, I don't understand a lot about it, so I will not go into details. But so these can, for example, be used as a control, let's say, when you want to compare, for example, with biopsies of people with tumors. Because the tumor will be completely different from this almost healthy control tissue. So but the idea is always reducing. This is what we always learn. This is what we always have in mind when we plan our experiments. And of course, we work in a lab that uses animal models. So we would need someone else actually that is less agreeing with it to go against us, or that to have the other. It's always important to have the two.
Did
two sides.
Did you already have some kind of vegan protest in your faculty saying, please don't kill the mice? I mean, is it something that happens, like, or?
We have no comment.
That's a yes.
Years ago,
yeah.
That's definitely a yes.
But I guess you never received, like, death notes saying you are
That's
killing.
right.
You are
Well,
killing.
actually, so 2 years, I think it was 2 years ago, right?
Yeah.
We had a very big problem in our university that came out on the news. So nothing that we're saying here is not, I mean, you can find it on the news, that actually a person was working in a facility that had the mice, right, and other animals. And this person actually belonged to a group. There was activists, right, in defense of the animals. And so this person leaked some images, and actually the image in itself, I can tell you, there was nothing there that was not approved. But the problem is, I mean, it's confronting. I mean, let's put it that way. What we do is not pretty. No, it's not. And if you guys see someone that is completely out of science sees this, I, for example, have every time I explain what I do, I'm very cautious about the way I explain what I do. Yeah. I ask the person actually in advance if this person is okay with me talking that I work with mice, I work with the brain, I inject cells in the brain. I mean, this is a bit confronting, right? I mean, we are not like serial killers or anything, but some people really take it as they do this without any care or anything, which is not true. I mean, we value a lot our mice. They are the ones who give us the answer. Yeah. They are the ones that make science go forward. So without them, I think it would be difficult to have so many drugs on the market just for a simple headache. Every time we have an headache, I mean, this is because researchers...
Yeah. That's a good point. When someone confronts you about that, you say, did you ever have like a headache or something? Yeah. And did you take pills? Yeah, you know how many mice we had to kill so that you feel better now?
Yeah, I mean... But
there are some, I can play devil's advocate. There are some tests that waste mice, though. So there are groups who study antidepressants. And they do the swim test in mice. So they put them in water and they see how long the mouse will swim until it gives up and is just ready to drown, at which point they save the mouse. And then they'll give them antidepressant drugs, and then they'll do this same test again and see whether they're willing to swim for longer, basically.
Wow.
But this also never rules out that the mouse just hasn't learned that as soon as it stops swimming, it'll be removed from the water. So there definitely has to be a push from both sides to improve the quality and the use of animals. And we should always, like with these tumor organoids and these other organoids that we can develop, this is also a step in the right direction because it means you use less mice because you can test something in an artificial system first. If it works there, then maybe you can look at it in mice rather than let's just start immediately with mice.
Yeah, that's actually another thing is that usually when we apply for these kind of like we call them ECDs, but it's just like a license, exactly a license. We have to say, why do we believe this is going to work? Did we try it somewhere else in, for example, what we call in vitro, but it's like in this kind of organoids or just in cells that are like in a plate? Or, for example, what they also suggest a lot that people do is that we share, let's say, these mice. For example, if I'm working in the brain and it's possible that Alex is working with the lungs, that we can share, right? That the most is taken out without me, for example, have to kill some mice and then Alex have to sacrifice others. So you see, so there are ways of getting things better. But of course, again, science, it is slow. Science is expensive, so it takes time. But for sure, we're not here saying, yeah, we should just use mice, forget the rest or anything. Because for me, for example, I have to say that when I felt more rewarding at my work is when I was able actually to work with human samples. So we get samples from the hospital, from people that are operated to a brain cancer, or for example, melanoma. I think you guys also had, we get biopsies, but we also get, for example, blood. And it's really rewarding when you can actually work with something that you think, hopefully this is really going to make an effect someday in these people. I mean, this is the people that are going through a lot. And if we can, in the future, make the life of these people better, I mean, this is what is most important, I think, in the end, following all the rules, of course.
Yeah, very interesting. I think it was a very good answer. So just to make a point of situation, we are talking for 1 hour, more or less.
And it's still going. No break.
Exactly. You know, I was like, you know, the 40 minutes passed. Zoom is still going on. I think I managed
No
to.
sponsors, no breaks.
Yeah, I managed
Till we
to.
got the sponsor.
As a digital champion, I managed to hack the system. No, I mean, I think I just want to do a point of situation. So we started talking about immunology, which is really the topic of our conversation, and we explained a bit what it is and how the immune system works and reacts for the different diseases. And then we entered a bit into coronavirus, into cancer, and how can our antibodies, part of our immune system, can forget what they knew before, so it's part of it as well. And then we also explained how immunology evolved over the time, and how we do research, why do we use animals, what else we can do so that we share the information about immunology and let's say scientific research to the broader spec of people, and not only the academia ones. And I think we can maybe talk a bit more. We still have time, and I wanted to ask you if you have something else that you feel like we should still talk, or if there is a topic that you wanna discuss further or go deeper.
Jeez.
All right.
Well, we've spoken about animals. That's and we can complain more about funding. That would be another nice one to survive through.
Well, I think we are all on the same boat, my friend.
Hey.
Anyway.
I wouldn't put pharmaceutical companies in the same boat as.
LAR is a non-profit organization, a very diverse and inclusive organization. It's not an organization. Wait, it's not an organization. Let's say it's a platform. It's a platform where friends come together and share with the world some things such as radio, DJ sets, live shows, talks like these ones, workshops. So I just want to say, if some people that is on the chat, that if they want to share some ideas, we are always open to that, for sure. If you have a hidden talent, I mean, just show up. We are here for you. But just to continue the conversation, I had a question about how immune a disease can be. For example, you were talking about, what's the name of that disease? Multiple sclerosis, for example. So
MS is actually...
Sorry?
No, go on.
No, it was I would like to understand a bit more this autoimmune disease, this immunodeficiency viruses and all this stuff, and maybe if you can give some examples of diseases that everyone knows, and explain how it relates to the immunology and to the immune system. It can be helpful for people just to have a picture on their heads.
Mm-hmm. So an autoimmune disease, an example of it is multiple sclerosis. I'm not an expert, so what I know is very basic about what, I mean, we read about what we understand. But so basically what happening here is that your body starts to think that your own self is not okay. So basically what our body does is that our immune system starts to eat literally our nerves. And our nerves are very important, as you know, for example, for locomotion. So one of the symptoms is that these people start to have a lot of difficulties to walk. So, and this is what happens in autoimmune disease. This means that actually our immune system starts to be reactive against what is ours. So, and that's, it's a very devastating disease when they progress very fast, because people can stop walking. And so you have, of course, relating now to the immune system, is that you can you can treat the symptoms, right? These people can do physical therapy, for example. But another thing is that you can target the immune system. And that's why it's so important to understand the immune system, is that actually you can act on it if you understand what is wrong, what is unbalanced. And in this case, our immune system, it's activated towards the wrong thing, right? So what you can give is, for example, immunosuppressors that will decrease this activity that our immune system has towards ourselves, and this can really help people getting better.
Yeah, so it's like your immune system, usually it's your friend, but sometimes it's your enemy. So if your immune system is your enemy, you need to take something to lower the amount of immune system you have, basically.
Yeah, basically. So, but of course, then these people also have to be careful, right? Because if your immune system is a bit down, they are more susceptible to other pathogens, right? Exactly. To other things that are in the environment. For example, another example that you have of disease are, for example, allergies. So allergies that are common, like, for example, allergies against grass, like in summer. So this is just because your body decided that, oh, this allergen, not good. We're gonna.
What is an allergen?
So, for example, grass, like grass or pollen. Pollens are an allergen, or for example, what comes from the grass. And then our immune system says, no, we don't like them. We're gonna act on it, and we're gonna stop this. But the problem is that while doing this and getting hyperactivated, what happens is that it can damage the tissues. So it can damage our own tissues. Like, for example, when people have allergy to peanuts, and if you eat peanuts, and then you can have you can start suffocating or something. So this is not good. So, for example, in case of just pollens, you can take, for example, what is called antihistaminics, because you have too much histamine in our body, so you just have to lower it down. So these are a few diseases that you can actually have because your immune system is unbalanced. Another example that you also have, if you want, but you have example.
Yeah. I mean, what I got from this second one, I mean, in the end is what you said at the start, right? So it's very important that the immune system is balanced. So if you start to be unbalanced, then you have a problem, basically.
Yes. So basically, just we try as your body tries as much as possible, and usually it works very well because at least the four of us, we are very healthy, so that's good. See, it can manage to help us and protect us from what is out there. But sometimes due to some things, like, for example, you have HIV. So it's a virus, right? And actually this virus attacks your immune system. And then your immune system is actually very low. So it doesn't have really a capability to answer well anymore. So, and this is bad, right? Because then you are very susceptible to simple things like just a seasonal flu that no one really has a big problem, right? Or even cardiovascular diseases. So they also make your body to be weaker, and you're more susceptible to to get other diseases. So.
And do you think we are close to resolve that? Do you think there is a line of sight for that, or
HIV?
Yeah, I would say that. Yeah.
Of course, there was the man in China who altered the genome of two girls that were born to mutate the receptor that the HIV virus uses to enter the cells.
What?
So
sorry, can you explain that, like, in a way that a normal human being like me can understand?
So there's a receptor on, I think it's on the T cells, right? On the cells that the virus tries to get into and attack and to replicate. And so it uses this receptor as a chaperone to be inserted into the cell, where it then multiplies and takes over the body. And so there was a Chinese doctor, I think, who altered the genomes of two girls while he was implanting them in a mother who was going through IVF. And he made this receptor on these cells no longer functional. So in theory, these girls are completely immune to HIV.
Yeah, because the virus tries to get inside the cell, but it won't be recognized. So that, like, it will go away. Those Chinese I haven't heard of, but I've heard. I'll be honest. I remember checking, but this was, I think, 1 decade ago. So
man, you are very old.
Yes, no, but actually it was 1 decade ago or more, perhaps. Because of the receptor for the HIV, and correct me if you heard about it or if you know something. There was some correlation with the receptor for the Black Plague that went. Have you heard of it, or how far-fetched this is?
You know, this is a very good example of fake news and how media is not sharing the
perhaps it is. But
no, I'm
but
kidding. I'm kidding. I'm just kidding.
But
something that can be conserved.
It can be. Yeah, I think it. Yeah.
Yeah.
But sorry, say.
No. I was just saying that it's much easier to use drugs or to use targets that are already in.
Of course.
I mean, in other diseases, and then you can just transfer
in
them.
terms of viruses and in terms of disease, our body has some of these receptors that are constantly funneled into cells, and they can be easily used to go in. So it can make some sort of sense that it's the same way to attack the body.
If you want to see it, let's say, just to make this conversation, I would divide this into cure and treatment, and that's because you talk about the cure, about the Chinese. If you want, this allegation would be that, and this is not an allegation, this is a fact. The Black Plague, I have no idea, but the fact is that there are people who are immune to HIV. It would be like close to no one. It would be 10 guys. I don't know. It's no one is, but there are a few small ones that are privileged in this world who are immune to HIV, and this. I'm 100% sure that there are recorded cases. I think that at the time they understood that this was in Germany, if I'm not mistaken, a doctor that spotted this. This was more than a decade ago. The theory would be the Black Plague, but who knows? Someone who had cancer and who had HIV. And they did a transfusion at the time.
They changed the bone marrow.
They did a transfusion, and they had no idea. They would do the tests later, and the treatment were not as advanced as they are now. 1 decade ago, a little bit more, and the person would always do negative on the test of HIV. Whoa. And that guy was in fact cured. The thing is, he's received blood of a guy who would be one of those who there are none who is immune. And this would be one of the possibilities. Of course, this is impossible to do on a large scale, but this would be one of the eventually possible cures of HIV.
Just make that guy bleed, you know?
Until, but he's going to cure like 10 guys and then he's dead.
But then
But this is a pretty story This is just if you want to talk about facts or something more, let's talk about treatments, not about cure.
Yeah, That's amazing.
That's a reality.
It's a very nice, nice story.
But if you want to be on a certain basis and something that we can speak more clearly and with non.
Oh, we could talk about successful treatments all night. And finally, you're the optimistic man.
Finally. No, but treatment nowadays, HIV, it's something that's
people can live with.
Yeah, people can live with HIV easily.
It's a chronic disease nowadays.
But for example, coming back to the case that you're saying that these people are immune, that's very true. But we cannot forget, and this is a bit related with COVID and people that may be immune. Because you are immune doesn't mean you are not a carrier. And this is very important for people to understand. So maybe you don't have the disease, but this doesn't mean that you may not transmit it to someone else. But this is just a bracket so that people get in mind.
No, that's good. That's good.
Yeah, it's very
doesn't
important.
mean that you are safe from, from everything, or you can actually be a hazard.
It is.
I'm not calling anyone a hazard. Sorry. Yes. But there are a lot of treatments for other diseases, like, for example, for cancer, we have immunotherapy.
There are some. So one of the cases we could have brought up was there are some people who have a mutation in their genome, which means they don't have an adaptive immune system. So they don't have the memory that an immune system should carry. So these people or I think most of their immune system is missing. And so these people have to live extremely sheltered lives away from basically away from the world. Otherwise, they can be at risk of dying from any sort of infection.
Or on those suits, like when you go to see some bees.
Yeah.
The bubble.
The famous one, was the bubble boy. And so this is quite a bad disease. And the way that it's usually treated is by a bone marrow transplant, which is where all of your immune cells are basically born from your bones. And so if you can remove all of this and then you can replace it with somebody else and their bone marrow. And so based on this, they can then get a correctly functioning bone marrow and return to some sort of normal life. But obviously this isn't possible because there are in a lot of situations, they can only do this from a sibling or something like this because there's not a lot of people who have such similar immune systems. So then you would immediately have, if you did it wrong, you would have the new immune system attack and kill this person, basically. And so very recently there was a group, I think they were using the HIV virus because it's very good at infecting and getting into our cells, to deliver the correct gene that reverses this disease. So I think they injected 8 kids with this and 7 of them had their immune system return to normal. They could start getting vaccinations. And then the 8th one was a little bit later, I think, but they all seem to be going quite well. So there are understanding the immune system. It leads
then they had HIV, no?
But they have an inactivated version of the virus.
Okay.
So understanding how smarter people than me learned how to manipulate with these viruses and alter them and remove the things that make them dangerous and then insert whatever they want to insert into them.
Yeah, of course, then we go to another topic, but it's a bit how vaccines, for example, can work, right? I mean, you inject a little amount, a little dose or an inactive virus, and then actually your body still can answer to it in a very lower scale, but be ready that when it sees the real threat to act on it. But yeah, I think this story was really amazing. I mean, when people put their minds into it, and when people really try to do research and to try to find new solutions, I think, people are really clever and intelligent. So it's really nice to see applying different things to different tools in a different disease with another disease. So
yeah, exactly.
It's nice.
And I think this is a nice transition to the question I have from the chat. They were asking to you and to Aleks, and I think then maybe I don't know if Jose you have more another question you can do, but then maybe we will wrap up. But the question was so. You are doing a PhD in immunology and in this area. What really drove you to do this? You know, like what type of light in the moment of your life you saw and you said, I want to do this, you know, like...
Okay. Do you want to start?
It's fine.
Well, that's very specific question, but okay. So I mean, since I'm in like high school, I had a very good teacher in like my last year of high school, and I had like molecular biology, and we talked about the DNA and how the DNA works and how the DNA controls most of the activities in our body. And because of that, then I decided that I would go into biochemistry actually, where I kept on studying like molecular and cellular things that happen in our body. And actually then I had the opportunity to, during my master, to do actually my master thesis in a lab that actually studies stroke. And there I actually entered in contact what is called microglia. Microglia is just a type of cell that it's the front line of defense of our brain. So, and they are a really cool cell, I have to say. And actually this is what made me be so interested about how is it possible that one cell in our brain can solve so many problems, not always of course, but can solve so many problems. And then I was actually just very lucky to actually find then a PhD where I work on exactly the same type of cell, but in a disease like cancer. And for me, it's a disease that affects all of us in some way. We all know someone that had, and so this is not just, at least for me, it's just not about immunology. Is one side the fact that I'm a bit nerd and I like to understand this cell and the molecular mechanism, but actually then what really drove me to continue studying immunology is how powerful this is to treat the diseases of people, like for example cancer, but not only, right? And of course, I'm quite focused on the brain right now, but I think all the knowledge that I gathered in the last years will allow me to work in the future in different fields, because actually the best is that we all communicate with each other and we share knowledge. But I feel very rewarded actually when I do, my job.
Is it true that if you unfold the DNA of someone...
That's Alex.
Okay, I can tell you my fun fact. Finally. So every individual cell in your body, if you took all of the DNA and stretched it out in one cell, I think it's more than 1 meter in length. And then if you took all of the DNA from every individual cell in your body and stretched it all together and tied them up, it would get to Pluto and out of our solar system. So this was one of the, well, not this specific reason, but it's fascinating the things that our body can do through these millions of billions of years of evolution. And it's fascinating. And so that was what drove me, at least, to science, is to try to understand a bit about, it's a very rewarding feeling having a question and then looking for an answer. Every day you get to just come in and ask a question and try to see what's happening. Usually that question is why or how. And then, interesting things come out of it, and then people take your results and then run with them and develop therapies. Just by all of the things that we've talked a bit about today have just come from people asking, why does this do this? And then knowing this, can we block it? Can we enhance it? And you get new therapies for many diseases, and it's quite a rewarding field.
And it's actually also the nice thing is that sometimes things that we find out are also by not accident, but a lot of big discoveries were done because people were working on something and then they found something else. But on the other hand, is also due to the work of a lot of years, but I don't know how long it was that. J.P. Allison, you won the Nobel Prize for also physiology and medicine for the immunotherapy. And I don't know, you know better, but he worked for so many years on trying to actually develop, put into trials.
I think it's basically a life.
His life. So
hundreds of people who.
Yes. So it's people that have their work is their life, but it's quite still noble, let's say, that this is done towards getting life of people there. Of course, I mean, we are always happy when we have good results, right? And I mean, it makes our day after so many not good results. But hopefully every scientist and every researcher does in the end this by the fact that they are curious, because they want to know more, because they want to understand better something. And on the other hand, towards, I mean, better knowledge that leads to better therapies and so on. So,
and getting a real job for me was a big motivator. I mean, I look at all of you guys. Anna's also trying to enter these other sectors. I don't like that.
Yeah, it's boring.
I can hang out in universities.
I mean,
everybody's all old.
That's creepy.
Okay, very, very good. I don't know, Jose, if you have something else to say, or if you want to ask some more questions, or just have your own close out of the discussion. And
not without a sponsorship, no. No, so we'll need to evaluate next time and see.
I mean, I think we both signed the pre-contract before this conversation, right? So I think that was
No,
that was quite clear.
You're good.
You were entitled to absolutely nothing.
That was loud and clear. Yeah, nothing to worry about.
You could give him a flag, Miguel, or give him some speakers for that bloody audio system above his head.
Yes.
That was already here when I moved in. So
put something on that.
Not the flags. The Portuguese flag I brought. The other one I bought. So, so yeah.
No, very good. Okay, so I think that's it for today. Thank you all for joining. It was a real pleasure to have all of you here. I think it was interesting to get the other side of the question, like having myself, the one that doesn't know anything, and having José that had a background on pharmacy, and it actually now working closer to the politics and so on. So it was interesting to see some discussions, and I hope that you also enjoyed. This conversation will be available on YouTube in a few hours, and we also have now a Spotify podcast channel. So if you don't really want to see our faces, just listen to it on Spotify, and make sure you follow us on Facebook and Instagram. And our platform is practically always live, almost every day, even if it is only the radio going on. But everything happens in our website, and we will keep on doing this, and we are open to new ideas and to new projects that you might want to show us, and then feel free to do that.
Maybe play some good music. Would be nice.
Yes.
No, I mean, this platform is actually going towards what we've been saying, a good way of sharing knowledge and on making people understand not only what we do, but other topics, maybe a future conversation will be, who knows, about politics. Exactly. And
lobbying. That would be nice.
Lobbying, who knows? I don't know. So it's just good. So this is all part of sharing knowledge and having people aware of what is happening. And so it's a really good initiative, I think. Congrats, guys.
Thank you. Okay. Thank you for joining, and have a nice of a day. Ciao.
Bye.